morning, ladies and gentlemen. Welcome to lecture 23. We will get started as usual with with announcements. So you know from Piazza and various sources that your exams are available along with solutions, score summary, regrading policy, etc. Look on Gradescope and look on Piazza. There are all the details there. Those of you who have looked will have seen that the class did just fine. The scores are essentially between 20 and 50. And the medians and so on are on the summary page. I took the scores, put them in a table, and did the summary using methods that you know how to do. So you should be very clear about what's been presented to you. If you have, let me talk a little bit about regrading. I learned this policy from David Friedman. So for regrading, all you have to do is give your name to the GSI. That's all they're going to take. You don't need to explain to them, and they won't hear why you want your exam regraded. They will give your name to me. I will regrade your entire exam. And the points can go up or come down or stay the same. What we have found is that students come to us with what they think are errors in a particular direction. They come to us with what they feel is an error that has given them less points than they feel they deserve. But you have to accept that correspondingly there may be the other kind of error as well. And so rather than grade an exam based first on what we see and then on what the student says we ought to see, our regrading policy is that simply we grade based on what we see. So you're welcome to give it back, and I will go through the whole thing again. I have never had a problem with this regrading policy. If students really feel that there's been something that will overall raise their grades, they come. Otherwise, they don't. So just look very carefully, not at the one problem that you're worried about, but at every other problem as well. I think the grades were assigned generously, so I don't expect too many of these anyway. If you got, in the 40s, that was a terrific performance. Well done. I looked very hard at the top. You would have noticed if you saw the score summaries at the top was 49. Now, if you look very hard at the 49s, each one of them had a different error. So it was genuinely 49. It was not us being mean. And so I thought about that because this exam was, I thought it covered what you had learned. I have not heard from students that it was, unduly mysterious in any way. Yet it turned out to be difficult to get 50. There were plenty in the 40s, but, and this has been a feature of my midterms for quite some time now. No single problem is terribly difficult, but to get the whole thing, you have to have mastered everything. And so, to the people who scored in the 40s, it's terrific. You have there are things that have come at you quite fast, and some stuff you learned very recently, and you have done very well. The rest of the class, I think you will perhaps be kicking yourself a little bit about this error or that, but that's fine. There's a learning curve in this class. For many people, learning all the coding in the beginning is a little difficult. As you have seen already, and as you will keep seeing, there's very little more coding for you to learn. You just keep using the same things over and over again. That is one of the reasons we've kept the midterm percent down quite low. It's only worth 10% of your grade. Each project is worth 10% of your grade. So from now on, what I ask that you do is you pay a lot of attention to the concepts and to the details of the code. Right? So the kind of sort of coding is great. We've done that. You kind of sort of know how everything works. And now you need to nail it down. You've got plenty of opportunity to nail it down. We are going to help by reducing the frequency of OK tests in your homeworks and so on, so that you actually have to think about why a certain thing will work and talk to people about it. And by the end of the term, I think you will be perfectly confident with the methods. So I don't see that you have any reason to change anything in particular. If you feel that you're doing a lot of work and not getting the result that you want, then please come and talk to us. Come and talk to me, come and talk to the GSIs, especially if you have a score below 20. This happens. Somebody has a really bad day on the midterm. The midterm is by far the most difficult day of the semester. In every course, Stat 134, Stat 20, it's by far the most difficult day. So it's not surprising that some people have a bad day on that day. The thing to do is to come and talk to us so that we can pick up where it is that you have obstacles and then work with you so that you enter the rest of the term with growing confidence. But for that, we need you to come to us. So please come to us. We don't feel that there is anything dramatic that anybody needs to change here. Sometimes students tell me, I will spend more time on this course from now on. My answer to those students is, maybe you don't have to. Maybe we just look at how you are spending the time that you are spending. And if we spend that better, maybe you don't need to spend more time. I don't believe necessarily that spending more time is always better. Right? We just need to see what you're doing and then make that more efficient. Perhaps you need to spend more time. I don't know. But also perhaps you can just spend your current time better. So the course staff are very satisfied with your performance. We think you have worked hard and done well. John De Niro took the exam the night before you took it. And he agrees that it was a perfectly reasonable exam and that you have done as a good class could be expected to do. So I'm going to shut up now and take questions. Grades, blah, blah, anything to do with the midterm. Yeah. Nope, we only did the quartiles. On an exam that's worth 10% of the grade, I don't feel that I need to do any more fine points. I am interested that nobody has asked me what was the 90th percentile of a project. It's worth exactly the same. So no, I think it's fine. I also did not do the mean and the standard deviation. We'll do that next week, and you will see that those are totally useless. More. So I would like to say a word about the solutions that have been posted. We were going to write solutions, but then as the GSIs were grading, I kept hearing these exclamations of, wow, this is a really good answer. And we thought, okay, we'll just take the students' own answers. And so the answers that you have posted as solutions were written by students during the exam. And we were absolutely delighted. Thank you. Those were wonderful. If no questions, can we get on with the rest of our lives? Don't dwell on the midterm, please. It's worth 10%. It's a little, learning experience for you. Okay, I get these things. I need to focus on these things, and that's it. We just move on. Okay, labs, as usual. No homework due this week. However, homework, as usual, assigned on Friday. You know all this. Okay, I have had a zillion emails about what other courses in data science are being offered. What should I take? So the first thing for you to understand is that Berkeley has been teaching data science for decades. It's just not been called data science. So there is a whole slew of things that you can take. Next spring in particular, there are a few courses that are being developed that have this one as a prereq. It's a pretty long, it's a couple of paragraphs that I have to write. So I will write that this week and I will post it on Piazza so that we don't have to have individual conversations with everybody. But if you are going to do data science for its own sake, that you want to learn more about data science and not using data science in a particular domain, but actually developing data science, then please make sure that you have programming, the CS61A series, linear algebra, matrices. You have seen tables, yes? One array after another after another. You got to understand arrays. So Math 54, preferably eventually Math 110, and a serious probability course. And then you have tools. So you got plenty to do to get ready. I'll talk more about the other classes. There is a class being developed that is focused not on those who want to go further into data science per se, but who want to use data science methods in other fields as well. So give me a couple of days and I will post something. There is one thing I do want to say. I have heard from a number of students that somebody has told them that in the year 2017 there will be a data science major. I would like to let you know that no faculty member on campus is aware of this. Not the directors of the Data Science Initiative, not the chancellor, not any provost, not me, not any faculty member. So if a student knows that this is going to happen, they know something more than the rest of us. I would take it with a grain of salt. Now, there's a lot of us working very hard to make this happen, but there is no timetable yet. As soon as there is a timetable, we will let you know. But in the meantime, I think you just have to prepare yourself as data. If you are interested in this, you have to prepare yourself as data scientists and hope that the university administration and bureaucracy and faculty also come together in reasonable time so that this all happens. This point I did want to make here. Some date is being thrown around, 2017. I haven't heard it. All right, shall we get on and do some work? Any general administrative questions? Anybody, anything? Okay, so last time we were talking about a method called the Bootstrap, and before I begin on that, what I am going to do is remind you that we had a rather large simulation that I did sort of in the background last time. Don't look at the code. I just want you to see, this is right here. I just want you to see that I am running it now. I'm going to go to Cell and run all above. And it's going to take forever, so a few minutes. So while we talk, it's going to chug, okay? All right, so a few reminders. We're trying to estimate a numerical parameter based on a random sample. Our random sample gives us one estimate. We are reluctant to simply present that estimate as our guess because we know that our sample might have turned out differently. So that estimate might have been different. And so we have to figure out, to give an honest estimate, we have to give a range of numbers. I just call it wiggle room. And so in order to find out how variable the estimate could be, we need another sample. So you've got to find some way of getting another sample. Now, typically, we cannot return to the population and take another sample because we've used up all our resources already taking the first sample. And so we need to find another sample from somewhere, and we notice that by the law of averages, the large sample that we have most likely resembles the population. So if we sample from that, we can get something else that resembles the population. Everybody remember this from last time? And so that's the Bootstrap. Here is a population. If we have a large random sample from that, then by the law of averages, this should look most likely like this one. And then the samples from this should look like this, which looks like this. So most likely all of these things should look about the same. And so we have a method by just taking one sample from the population of generating many more. Now the object of generating many more is to compare, is to quantify the variability in our estimate. So the new samples that we take have to have exactly the same size as the old one. If you are looking at the median of a sample of size 500, then you should compare it to the medians of other samples of size 500. And for that reason, you take your sample, supposing it had size, I'm just going to use some other size, supposing it had size 1500. From that sample, you want to take another sample of size 1500. How do you do that? Well, not without replacement, because you'll get the same thing back again. You sample with replacement 1500 times, and you get another sample. And the wonderful fact of math and probability and statistical theory is that this actually gives you a good method of generating a new sample and generating intervals. So all of this is recap from last time. I'm going to pause before I get to the notebook. I'm going to pause and take questions. And so I'm going to do a quick run through of where we were. So, okay. We had a table of total compensations. Why am I running these again? Okay. Of San Francisco city employees, and our parameter of interest was the median. Now, those data, that histogram is for the entire population. This median is for the population. Therefore, we know the parameter. Therefore, from a practical perspective, we would not take a sample at this point. We just know the parameter, we're done. But in the end, we'll have just a sample, and we won't know what the population is like. We need to see whether our method is any good or not. So what we're going to do now is we're going to take a sample from this thing, develop a method of generating estimates, and then, because we happen to know the parameter, we can check whether our method's any good or not. So we did that last time. Do you remember this? So even though we had the population, we did this calculation and we tucked it away, and then we took one sample from it and just made our estimates based on that sample to see how good the method is. And so quick run through. You take a sample, you look at its distribution, you look at its median. Okay, so I got 108,000. The actual median was 110,000. No surprise that I got somewhere close, but not exactly. Now, so that's one estimate. And now what does the Bootstrap say? How do you get another estimate? You need another sample, so you resample from this thing. I want you to look at the code here. Please explain to me what has happened here. So this is the original sample. It's a table. And so we use .sample. Why is there nothing in here? There are two defaults that are being used. One default, please. Yes. If you do not specify a sample size, it samples exactly the same number as you have rows in your table, which is exactly what you need for the Bootstrap. It samples the same number as you have individuals in your original sample. That is good. And what's the other default? Width replacement equals true is the default. That is exactly what you need for the Bootstrap. Okay, so that little piece of code gives you your first resample, and the distribution of that resample looks like this, which kind of sort of looks like this, which kind of sort of looks like this. This is no surprise. This resample has a median, which is 111.5, roughly. Okay, so again, around our population median, but not quite equal. So obviously, if you can do it once, you can do it twice. And you get something else again. And so we know you're going to do it again and again. So let's just spend some time. This is our old function. Bootstrap median takes the name of the table containing your original sample, the label of the column, which is your variable, the number of times you want to do the replications. It first extracts the column of interest from your table just so that you're not working. Sometimes the tables are huge, right? There are vast numbers of columns, and you're just interested in the one. So just to save some computational time, just extract the one. And then it starts with our parameter of interest is a median, so the blank array of results is called the medians. For every replication, you take your column from the original sample and you sample from it for the Bootstrap. That's your Bootstrap sample. You compute the median of that sample. Please recall the method percentile takes two arguments, a rank, which is a number between 0 and 100, and an array. That is why we have Bootstrap sample.column. And that is your resampled median, and now you collect, using np-append, the new median into your array of medians, and the function returns the array. So ready to roll? This is all old stuff from last time. I'll pause before we run this. Questions? Okay, so what this is going to do is 5,000 times what we just did 2 times. We did one resample, got the median, then we did another resample, we got the median. We're just going to do it 5,000 times. Yes? Why do I have to specify the column if I'm only I'm taking a sample? Oh, this? Because, okay, so the question is, why do I have to specify a column if there's just one column? Because .sample, bootstrap.sample is a table. Yes? It's only going to have one column, that is index 0, but I need to convert that to an array. Right? Percentile, the second argument, is an array, not a table. Okay, so we're going to run this thing 5,000 times. And you can see that star for a little bit, and it's done. So what has happened at this point? Yeah. We've made an array, thank you, of our how many? 5,000 bootstrapped median values. And so I'm going to put them in a table because I want to draw a histogram later, and .hist is a table method. So now we had discussed, so you got 5,000 medians. Which of those are your estimates? We had discussed one method that says just take the middle 95% of them. Yep. So to take the middle 95% of them, we have to take 2 percentiles. Which percentiles are those? So we're saying 95, it could be any other percentile. So in the head, middle 95%, on the outside 5%. Yes? So 2.5% on either side. Therefore, the left end is the 2.5 percentile of our 5,000, which is 1,000 and which is 102,000. The right is 97.5 because it's 2.5% on the right-hand side. So you're subtracting 2.5 from 100. And that came out to be 113, and so here is a visualization. Okay. That histogram is a histogram of our 5,000 resampled medians. The yellow segment there is the middle 95% that we just computed. That red dot is the thing that we have pulled out from our back pocket. What is the red dot? The population median that we actually happen to know. Right? In real life, you will not know that thing. But we're just doing an instructional demonstration here, right? So you know that red dot, so it's in there. So that is a good interval. That interval of estimates contains the parameter. It is very important that you recall that the parameter is fixed. The red dot is not moving at all. It is the interval that is random. So it is the yellow interval that could be sliding around. Yeah. Why did I use 95%? Because it's a number I got off the top of my head, and because it is the most commonly used percentage. However, in just a moment, we will use other percents. So the 95% interval says, okay, I'm willing to jettison 5% of my observations. That's kind of parallel to Fisher's 5% p-value cutoff. That is why 95% and 99% are very commonly used. So, all right. So what has happened at this point is that we have generated one interval of estimates. In this case, our interval happens to contain the red dot. Of course, had we got a different sample and run the process again, we'd have got a different estimate, and that may or may not have contained the red dot. Agreed? And that is why we were running this massive great simulation here that basically does what we have just done, that one interval, but does that 100 times. Okay? So what this does is it's going to generate 100 intervals. So what is it doing? This here is the population. It is the total compensation column of the original table. The original table had something like 37,000 rows in it. Right? So that is a very long column of total compensation amounts. What it does is it repeats the entire process. it first draws a random sample of size 500 from the population. Why 500? Because that was the sample size we elected to take for our previous sample. Then it gets 5,000 bootstrapped medians from that sample. That's what we just did from our original sample. Then it finds the left end and the right end of the middle 95% interval for that replication, and it sticks them in the appropriate arrays. And that's one interval. That is what we just did. And then it does it again, another interval, again, another interval, etc., 100 times. At the end of this simulation, we have 100 intervals. Everyone clear? So now we will take a look. It has finished chugging. We will take a look at what the intervals looked like. And there's 100 of them. So I'm going through what was my actual amount was 110 something, right? So this one contains it. This one's bad. You see? Third one's bad. So some of them are bad. Most of them are good, as you can see. So how many of them are bad and how many are good? Well, why don't we just count? So a good interval is one where the left end is below the population median and the right end is above. Agreed? Okay. So here's the moment of truth. 91 of them were good. So what we're expecting is something around 95%. There are many approximations going on here. You typically, unless you are quite unlucky, you will get a number of good intervals somewhere in the low 90s to the high 90s. Okay, to visualize what has happened, what I have is a cell where I really don't want you to think about the code when we have this. Okay, so I want you to take a look at what has happened here. Those 100 intervals that we've drawn are all on the horizontal axis of the histogram, right? So if we just drew it all there, you wouldn't be able to see anything. They would be on top of each other. So what I've done is I've stretched them out. This right here is interval number 1. This is this is dollars. This red line is the true value, $110,305 roughly. Yep. This is the first interval, which goes from, what does it look like? That's 105, so it's going a little bit below to a little bit below 115. Let's see. What do we have here? Yeah, so about 103 to about 115, roughly. That's the first interval. That's the second interval. That's the third one. That's the bad one. Yep. So a good interval is a one that covers the parameter. If it covers that red line, if it captures the parameter, it's a good interval. If you can see daylight around the red line, you've got a bad interval. And what you are seeing in this is that you have, I see 1, 2, 3, I can't tell this one, 4, 5. How many bad intervals do I have? 9. 9 of these are bad. The reason for drawing this picture is to remind you that the true value is fixed. It's the intervals that are random. And sometimes they capture the true value and sometimes they don't. What you are seeing is that this method captures the true value the overwhelming majority of the time. So somebody asked, why 95%? Well, having chosen 95%, we expect around 95% of the intervals to capture the true value. Had we done 80%, what would we have got in these? Roughly 80% would have captured the true value and 20 would not. Okay, so I'll pause and take questions on this picture. Yeah. Precisely. This picture is helping us, I wouldn't say prove, I would say it is helping us demonstrate that this method of generating intervals using the Bootstrap is a reliable method. And it's not just that it is reliable, that we can quantify the reliability. that it gives us a good interval approximately 95% of the time. Now, there is a world in that word approximately, and that's why you take statistical theory. But for now, you expect somewhere in the 90s the good intervals if you use this process over and over again. Okay, so no questions, okay. So what we're going to do now is we are going to do inference using the Bootstrap. The difference between what we're going to do now and what we have done thus far is just that we won't know the population. That's the typical scenario. You have a huge population and you've taken a sample from it. Your data are only from the sample. You don't know the population. But because of our old picture, we know that the sample, because we have taken a large random sample to start with, the sample most likely looks like the population, and the resamples most likely look like the sample, and therefore all of these guys most likely look like this question mark. The only difference here is that we are not going to be able to test whether our interval has the parameter in it, obviously. The whole point is we don't know the parameter. So this is where you rely on the demonstration and also on mathematics that establishes the Bootstrap as a reliable method of generating an interval. And so you produce an interval of estimates that is known, and I'm sticking with 95% for now. We'll change the percentage in just a moment. It is known as a 95% confidence interval for the parameter, and that is jargon for a simple word, estimate. It is an interval of estimates for a parameter. So you think that the population median is in that range. That's what you're saying. It is based on random sampling. Do not construct confidence intervals based on samples that are not random. The theory doesn't apply. Okay, 95%, that number has a name. It's called the confidence level, and so we'll be changing the confidence level shortly and seeing how things change. That can be any percent between 0 and 100, not 0 and not 100. You wouldn't want a 0% confidence interval. I mean, if I'm estimating the median salary and I say, well, my estimate is, I don't know, minus $1 million to minus $5 million, that is probably a 0% confidence interval, but I'm really not interested. 100% confidence intervals also, I mean, you can actually create them, but they're not interesting. If you want a 100% confidence interval for this particular median total compensation, how about minus $3 million to plus $14 million? That median's going to be in there. You've got 100% confidence. You've learned exactly nothing. So based on a random sample, what you're trying to do is to get close to this median, right? To get close, you want the interval to be tight. Now, the tighter you make your interval, the less confidence you have in it, right? So there's always this give and take. Your level of confidence versus the narrowness of the interval, there's always a give and take, and that you have to decide what level you are willing to accept. For now, we are going to stick with 95%. Bigger is better in the sense that you have more confidence in the interval. On the other hand, the interval gets longer. The middle 99% is just simply longer than the middle 95% of the same resamples. All right. So the confidence is in what? The confidence is in the process that generates the interval. You have seen that process gives you a good interval approximately 95% of the time, if 95% is the level. If the level was 70%, then it would give you a good answer about 70% of the time. So the method that we're using is called the Bootstrap percentile method, and it does exactly what we've done before. What is it for? It is for constructing a confidence interval. When you hear those two words, confidence interval, you should do a translation in your head. Your head should say estimate. It is for constructing a confidence interval for an unknown parameter using the following method. The starting point always is one large random sample. If you have anything else, if you have small or non-random samples, all bets are off. You create a replicated estimate by bootstrapping that random sample once and getting an estimate based on that resample. and then you do this many thousands of times. There is some theoretical justification for 10,000. I've been doing 5 just because I don't want to wait forever for these things to chug. But there are many experts who feel that 10,000 is probably a good. There's obviously, it depends on the particular situation. Okay, this gives you 10,000 different estimates. And so now, for an approximate 80% confidence interval, you take the 10th and 90th percentiles. Let's just check that we agree with that. 80% in the middle, therefore 20% outside. So we'll go 10% from below and 10% from above. 10% from below is the 10th percentile. 10% from above is the 90th percentile. All clear? Any level of confidence, you know how to find a bootstrap confidence interval. Okay. So I'd like to do this now for a data set which is a random sample of mother-baby pairs from a hospital system. And there are various variables on the newborn. So there's the birth weight in ounces. This is the number of gestational days. This is the mother's age in completed years, height in inches, pregnancy weight in pounds, and whether or not the woman is a smoker. There was plenty of other data as well. There's data on the fathers, all kinds. We are going to be interested today in one variable, which is birth weight. It is important to have some sense of a baby's birth weight because smaller babies just tend to have a slightly increased likelihood of problems initially. So one of the things we're going to do is to see if we have a relation between birth weight and gestational days. You kind of know how many days the mother has been pregnant, so can you say anything about birth weight based on that? And we're going to use the simplest possible relation. We are just going to look at the ratio of birth weight to gestational days. So I'm going to select out the first 2 columns. This is birth weight in ounces. This is gestational days in number of days. And I'm going to compute the ratio. So this one here is 120 divided by 284, and its units are ounces per day. Right? So at a very rough estimate, for every day of gestation, the baby has about 0.422 of an ounce of weight. Let's take a look at that variable, and I want you to remember, please, that this entire table is a sample. It's not a population. There were 1,174 rows in this table. So the sample size is 1,174. What we're going to do, just to get a sense of that variable, is draw a histogram of that variable. And that looks like that. Most of the action is just around 0.4 to 0.45. Most of the babies are there. There are some that are out here. And because there are some that are out here, what we are going to take a look at is the median in the population, because the median doesn't care what's out in the very big end or what's out at the very low end. It all depends on what's happening in the middle. So it gives you a better sense of what's typical. Okay? So we are going to look at our parameter. Our parameter of interest is the same parameter that we used in our previous exercise, the population median. The population is the population from which these mother-baby pairs were drawn. That has a median that we do not know. We're going to try and estimate it. The natural first estimate is the median of the sample. So ratios has columns 0, 1, and 2. Our variable is in column 2. The median of that is about 0.43 ounces per day. So half the babies had these ratios of 0.43 ounces per day or less. Okay, so now we are going to bootstrap. And what are we going to use? So I want to bootstrap 5,000 times and generate 5,000 different medians. What are we going to do? We've got a function. It is called bootstrap medians, yes. It's somewhere. Right here. Yes? Bootstrap median takes the name of the original table, the label of the column you're interested in, and the number of replications. So now I've lost my place entirely. So we're going to call Bootstrap singular or plural? Singular. Okay. Name of table is ratios. Name of column, I gave it an awful name. Okay. Ratio birth weight to gestational days. So ratio birth weight to gestational days. And I've said in my comment that we want 5,000 of these, so we're doing 5,000 of these. And if I just do that, it's going to split out 5,000 numbers as an array on my screen. That's not helpful. I want to capture them somewhere. So I am going to capture them in Bootstrap medians. How about that? Right? I will end up with an array called Bootstrap medians that has 5,000 medians in it. Ready? So why is this taking longer than the previous one? It's done now, but it took a little bit longer than the previous one. Why? Still 5,000 replications, but sample is larger. Sample is about 1,200 as compared to the 500 before. Right? So you're resampling. There's just more going on. Okay. So now we are going to get the left and right endpoints of a confidence interval. We are going to use percentile. Okay, left end, which percent? 2.5, and the array is called Bootstrap medians, and this one is 97.5, and that's called Bootstrap medians also, and we run that, and your confidence interval is 0.425 to 0.43. One of the things you might do as an exercise, the one we got from our original sample was 0.429. It happens to be about exactly in between. That's not necessarily the case, but it was going to be typically almost in between. Okay, let's take a look at what this looks like. Okay, these are our 5,000 medians, and there's your interval of estimates. So you are saying that the median ratio in the population is in the range 0.42, whatever it is, to 0.432, whatever it is, with 95% confidence. Now, so if you imagine, had somebody who had the population done this over and over again, they'd have got 100 intervals, 95 of them roughly would have been good, and 5 of them would have been bad. You have no idea which one this is, right? One of the things to note is that it's a fixed interval. It is 0.425 whatever to 0.432 whatever. The population median is a fixed number. So this interval either contains that population median or it doesn't. It either always contains it or it never contains it. It is not the case that it contains it on Mondays, Wednesdays, and Fridays and not on Tuesdays and Thursdays. You are talking now about a fixed interval and a fixed number. So you can't really talk about chances. The chance is either 0% or 100%. Your confidence is in what? Your confidence is in the process, right? You're kind of betting on this interval. It may be a dud. You don't know. But you know that your process is certainly better than guessing at random or any other method. And every time you make an inference based on a random sample, you are faced with this prospect that you have some possibility of being wrong. And indeed, every time you make an estimate based on any kind of sample, you have some possibility of being wrong. The good thing about random samples is that you can quantify how likely you are to be wrong. Okay, what we can do for medians, we can do just as well for means. So the parameter that we have used thus far in almost 2 entire lectures has been the population median, but you can play the same game for means. What I'd like to do is I'd like to estimate the average age of the mothers in the population. This histogram is the histogram of the ages of the mothers in the sample population, which Sample, that's all we've got. We do not have the population. This is the histogram of the 1,174 mothers in our sample, their ages. Okay. And you can see there's quite a variation. There was one very young mother, 15, and then there are some out in their 40s. There's quite a variation in ages, and that distribution is pretty typical for age distributions of populations. It sort of tails off on the right-hand side. All right. So our parameter of interest is the average age of mothers in the population. How much is that? Average age of mothers in the population. What's your best answer to how much is that? Best answer? I have no idea. That's your best answer. You do not have the population. That thing there is the sample. You do not know it. That's precisely why you're trying to estimate it. So that is an unknown parameter. What you do have is one estimate from a sample, and in your sample, the average age is around 27. Great. So in this sample, it was around 27. In another sample, it might be 26 point something. You don't know, right? So you need to take another sample. So you need to do what? You need to bootstrap this sample and compute the mean, not the median, of the new bootstrap sample. And so you need to define a function called bootstrap mean. All agree? So we are going to cut and paste our old familiar function, if I can find it. All right, that was I want a mean. Same input. Table, which column, how many replication. I'm going to get an array of means. I am going to select a, that's why all I've done is change names. I haven't changed any calculation. Okay, so I'm going to select my column of data. I am going to now change a name again, and now I am going to bootstrap my sample. I have changed nothing. Now, here, I was computing a median. I will compute a mean instead. So np dot mean. All right, that goes away. That's the array. That's a resampled change name again. That's a resampled mean. Append it to the array of means. So I hope you all agree that every single change except one that I made was a change of name. Right? The only thing that was a change of computation was the percentile, 50th percentile became a mean. That's all. We're doing precisely the same thing apart from that. Okay, so that's my definition. Questions? Yes? Okay, so okay. Finish calculation, then general question. I'll have a lot to say about that on Friday. The question is about the connection between p-values, cutoffs, and confidence levels. Okay, so we have that, and we are going to now call our function. Bootstrap means the table is called baby, the column is called maternal age, and we are going to do 5,000 replications. And we are going to get a an array of 5,000 means. Okay. How about we do, why 95%? How about we do 80? Or, well, actually, no. You tell me what percent. 75. Okay. You would choose one that has a 5 in it. Okay. Okay, so I need 100 minus 75 divided by 2. That's the amount in each tail. You agree? So this thing is the 12.5 percentile of Bootstrap means. This thing is the what? 87.5 percentile of Bootstrap means. And that's my interval, and that is our visualization, narrow interval, less percent. I want you to notice something. See the shape of that thing? Yeah, you see a bell shape? Look at the shape of the original data. Bell shape? No. Okay, there's something going on there. I'll see you Friday.